We've been talking about types of reactions, and last time we talked really about one sort of specific type of reaction, which is double displacement reactions. And remember, in double displacement reactions, we basically have two ionic compounds. And what always happens sort of in this reaction is the two positive guys again will basically switch partners. And as they switch partners, they will form two new ionic compounds on the other side. In this particular example here, A and D, and C and B. Now, double displacement reactions, as we talked about, is sort of the big classification of reactions for which you can also get a lot more specific in terms of ways of classifying double displacement reactions. So really two kind of specific classifications of double displacement reactions are a precipitation reaction . And in a precipitation reaction, some type of solid is formed. So one of these guys, as we also talked about solubility rules, one of those guys, when they do come together, those two ions, they do make a solid. Another sort of classification that falls under the double displacement reaction is the acid-base reactions. And in acid-base reactions, basically one of the main things that happen is really the formation of water. And the formation of a solid and the formation of water are, again, really, kind of two of the three reasons why some reaction takes place is one of those two things happening. Today as well, we will add sort of the other big sort of category of reactions, which are redox reactions. And redox reactions basically take place for electrons to be transferred. So the transfer of electrons. And really those three things, as we talked about, a transfer of electrons, a solid being formed, and really formation of water are once again really the three sort of reasons a reaction takes place. You can almost kind of break it down to pretty much those three things happening. We also talked about some important types of equations, those being our molecular equation, where we write out everything in their proper formulas, like silver nitrate plus potassium chloride makes a little potassium nitrate and silver chloride. And here, this guy being a solid precipitation reaction, double displacement reaction. Again, here, this is a positive, negative guy, and on the other side, again, the two positive guys basically switch partners to get there. We also can write an equation which does represent sort of what happens when we throw these guys. Yeah. Redox. So redox. Other questions? So we also can write another type of equation here that really sort of describes what happens when these guys go kind of into the beaker. And this is what's sometimes referred to as the total ionic equation. And the total ionic equation, we basically break apart anything that's considered a strong electrolyte. Remember, electrolytes are guys that go into solution, break apart, and basically produce ions and can conduct electricity. Anything that is a weak electrolyte, anything that's a solid, liquid, or occasionally a gas, if you come across it, should stay together. So for example, here, the silver nitrate would break apart into a silver ion plus a nitrate ion. The potassium chloride would break apart into a potassium and a chloride. Potassium nitrate would also break apart into a potassium and a nitrate. And I'll just write it underneath here. Again, the solid here would stay together. This basically represents sort of what's going on when we kind of dump this guy into, like I said, a beaker. We usually in this sort of equation here can find what are referred to as spectator ions. And spectator ions are guys that are ions on both sides of the arrow that look exactly the same. So we have nitrate and potassium in this case. These guys are spectator ions. And what we're left with after we usually will cross out the spectator ions because they are really not there to make any type of product or anything like that. We're left with the third type of equation, which is important, which is referred to as the net ionic equation. And that gives us a silver ion plus a chloride ion, and that makes silver chloride. And really the net ionic equation, as we talked about, is pretty much the equation that really cuts down to the heart of the matter of what is actually happening in this reaction as you basically mix those two reagents together. Is really in this particular example, the silver from the silver nitrate, finding the chloride from the potassium chloride, and they're making that solid, which is our silver chloride. Any questions on any of that stuff? I think we talked about last time, yeah. Okay, so did we talk about acid and base reactions or did we not? That's not where we stopped. Anyone? We did? Okay. All right, so just to be sure, we'll make sure. So a reaction of an acid and a base will always really produce water. And that again is one of the reasons why a chemical reaction takes place. An acid is really, again, a reminder, anything that can produce H plus, and a base is basically anything that can produce hydroxide. And whenever you take a strong acid plus a strong base, you basically get a salt and water. And obviously a salt is an ionic compound. So for example, if you took something like nitric acid, which is a strong acid, and react it with KOH, which is a strong base. This is also a double displacement reaction. We got plus and minus, we got plus and minus. So the H plus and the OH will come together. The K and the NO3 in this case will come together. And we will get KNO3 plus our H2O. This here would be our salt, and this would be our water, obviously, in this particular case. So acid-base reactions are also sometimes called acid-base neutralization reactions because they basically form water. And it is really still just a double displacement reaction. Remember that for an acid, pretty much the cation is always H plus, so we consider it really like an ionic sort of compound. We could take this exact same molecular equation here and break it apart into our total ionic equation, which would give us H plus NO3 minus would give us K plus and OH minus. On the other side, our K plus and our NO3 minus will break apart. And once again here, because water is a liquid, it will stay together. So this gives us our spectator ions like we saw previously. And in this particular case, it is the nitrate on both sides and it is the potassium on both sides. Those guys will cancel out. And it will give us our net ionic equation. Basically H plus OH minus is basically making water. Pretty much no matter what combination of strong acid and strong bases you put together, that's your net ionic equation. That's going to pretty much be the formation of water is going to happen. Again, with a strong acid and strong base, that is what will happen. If you had a weak acid and a strong base, your net ionic equation would be different because a weak acid is a weak electrolyte and would not break apart. So for example, it would look slightly different if we took something like HF and KOH. This would give us KF and H2O as our molecular equation. Now, HF here is actually a weak acid. So what that means when we would get to the sort of total ionic equation, because it's a weak acid and a weak electrolyte, we actually would keep it together. So remember, weak electrolytes basically stay together. So we would actually not break apart the HF in this case, because it's a weak electrolyte. We would still break apart the K plus and the OH minus from the strong base. We would also break apart the K plus and the F minus from our salt there. Get this out of the way here. And we would then also have our water, which would stay together. In this particular case, when we go to look for spectator ions, because we do have that weak acid or weak electrolyte there, we actually are only going to find one spectator ion in this case, and that is going to be just the potassium. And that would be the only thing that would cancel out. So you would end up actually with a net ionic equation that looks something like this. So a little bit different than what we see with a strong acid and strong base. Again, the weak acid, because it's weak, it will still be there. You don't break it apart. Any questions on that, though? Yeah. So I think we made it last time, and I'll put it up here just to make sure. But there's kind of a list of like 6 strong acids, and pretty much if it's not one of those, it's probably a pretty safe bet to assume that it's going to be a weak acid. So some strong acids. HCl, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, hydriodic acid. Just kind of like a 6-pack there of pretty strong acids. And like I said, for the most part, if it's sort of outside of that list, I would say you're probably a pretty safe bet that's going to be weak. Some common weak acids that you do come across. HF is a common one. Acetic acid. It's a very common one that you come across a lot, and it's sometimes written a couple different ways. Nitrous acid, HCN, carbonic acid. So those are some weak acids, but I would say probably the easier move is just to really understand which ones are definitely strong acids. And like I said, probably 9 times out of 10 or even higher than that, you'll be in good shape. It's probably safely to assume that it's a weak acid at that point. Other questions on that? So again, here is our hydrochloric acid plus sodium hydroxide. Once again, this is a strong acid and strong base. And remember, strong bases, by the way, again, are kind of group 1 and group 2 with hydroxides. So like sodium hydroxide, potassium hydroxide, hang a right over there to calcium, strontium, all those guys with OH in the actual formula are a lot of strong bases. Again, really a double displacement reaction, positive, negative, positive, negative. So once again, these guys are going to basically switch partners. And it always is really the H plus from the acid, the OH minus from the base in this type of reaction. That really is where water comes from. So really to get the salt in this case, you could just, cross out those 2 things and then put those guys together correctly. And that would get you obviously your correct salt in this particular case. Once again, when we break this apart, what we will see is we have chloride and sodium here that are our spectator ions. And we would again cross those off. And once again, you can see in this one, just like the previous one, that is always the end result pretty much of your strong acid, strong base reaction. Yeah. In this particular reaction, yeah. So really, if you think about kind of double displacement reactions, whereas a lot of times where we write net ionic equations, we also do for redox as well. But really, the two main things that happen in double displacement reactions are you make a solid or you make water. So your spectator ions will always be the things that don't make water, and the things that didn't make the solid are basically the ones that always be spectator. They also should, by the way, always completely cancel out when you get to the total ionic equation. So if you get to a point where you have, say, 2 chlorides on the left, but only 1 on the right, something's not right either with a formula or how you balance the molecular equation, because they should always completely cancel out at that point. So it's a good way to check yourself. If you get to this part here in the middle and you're like, they don't completely cancel out, probably something's wrong with the balancing of what you did there. Other questions on that? All right. So again, here's just a couple other things. I would say in most cases, the salt a lot of times will be pretty much soluble, because a lot of, again, strong bases come from group 1, which is based on our solubility rules that we talked about, pretty much soluble in everything. So most of the time, the salts will usually end up being soluble. It is occasionally possible you could get an insoluble salt, but probably not too often because of that. All right, so officially, just in case we didn't do acid base, any questions on double displacement reactions? Okay, so what we're going to talk about now is really the rest of the type of reactions, a lot of which we did in that experiment the other day. But all these kind of fall under the next big category, which again is redox reactions. And redox reactions do stand for oxidation reduction reactions. They're sometimes shortened for redox. And when we talk about oxidation reduction, they do have several types of meanings. And redox reactions, again, are sort of the big umbrella for which other reactions sort of fall underneath. Oxidation, as we will see, basically has a definition of losing electrons. And reduction has a definition of somebody that has gained electrons, basically. So if something goes through oxidation, it means it has lost electrons. If something goes through reduction, it has gained electrons. The good thing about these type of reactions are they always occur together, which means if you could identify who was being oxidized, by default, the other guy is being reduced, and vice versa. So that's kind of the nice thing about it. Also, the transfer of electrons here are always perfect transfer of electrons, which means whatever electrons somebody loses, however many somebody loses, should be the exact same number of electrons that somebody gains. So there should be that kind of perfect transfer of electrons from one place to the next. A couple of other definitions of oxidation, which we won't use too much in this class unless you go to organic, is the gaining of oxygen from reactants to products, are the losing of hydrogen from reactants to products, and reduction would be the opposite, the losing of oxygen from reactants to products, are the gaining of hydrogen from reactants to products. So in organic chemistry, a lot of times we use these definitions because for the most part, we're dealing with a lot of nonmetals. So sometimes it's easier to look at sort of gaining or losing hydrogen or oxygen. But really in general chemistry, the losing of electrons, the gaining of electrons are really sort of the definitions that you come across the most. Again, when you get to organic, you'll kind of see those other ones. So let's talk about what happens when somebody loses electrons or gains electrons, and how we can sort of figure out, is somebody going through oxidation or reduction. One thing that we look at is what is known as the oxidation state, and is sometimes referred to as the oxidation number. And the oxidation state or number is really what the element has in terms of a charge in this particular situation. So what I mean by that is, in an ionic compound, the oxidation states are pretty much the charges everybody would have. So like, sodium is +1 or chloride is -1. In covalent compounds where we're sharing electrons, elements take on different sort of charges based on who they're sharing electrons with and how many they're sharing electrons with, the electronegativity difference of everybody they're sharing electrons with. So sometimes things that we normally think about in sort of an ionic compound situation, for example, like chlorine, we typically think of chlorine as always being -1 in all situations. And it is definitely -1 in a ionic compound. So when you hook it up with a metal, it's definitely going to have basically a -1 oxidation state. But when you hook up, say, chlorine with a couple of oxygens or 3 oxygens or 4 oxygens, the chlorine actually will take on a more positive sort of charge because it's hooked up with oxygen, and there's a difference in electronegativity and how they're sharing electrons. So oxidation states or numbers are not exactly the exact same thing as we think about when we think about charges with ionic compounds, but they do help us a lot to understand whether or not something is being oxidized or reduced. And there's sort of a simple way to sort of figure that out. And you could take like a basic number line here, and usually to the right there is positive numbers, right? To the left of 0 is negative numbers. And if something loses electrons, will they become more positive or more negative? They will become more positive, right? Because they lost electrons, they have more protons. So what happens is if you look at where that element started to where it ended, and if it's moving in this direction in terms of its oxidation number, becoming kind of more positive, that means it is going through oxidation. And obviously the other is true. If somebody gains electrons, that means that they are going to become more negative than they started with because they have more electrons than protons. So if you follow the oxidation number of some element and it's heading in this direction, becoming more negative, you can go through reduction basically here. So a couple of simple sort of rules to follow when assigning oxidation numbers or oxidation states to help you through some of these is any element that is by itself uncombined, sort of how it naturally comes, has an oxidation number of 0 basically. Oxygen, for the most part, will always have an oxidation number of -2. Hydrogen will be +1, except if it is hydride, which then it would be -1. Fluorine always has an oxidation number of -1. And there is an exception for oxygen, which is actually peroxide is -1. So if it happens to be peroxide, which is not oxygen, it would be -1. So those are some kind of simple rules to help you decide what is being oxidized, what is being reduced. So for example, if we took something like magnesium, like we did the other day, I think, we did a little O2 action, and we made some magnesium oxide, right? So when we look at the oxidation states here of each of these sort of elements on the left-hand side and the right-hand side, we could assign sort of our oxidation states. And for example, magnesium, that is just the element by itself. It's uncombined, which means it falls in this category. It basically has an oxidation state of 0. So it has no charge or nothing like that. O2, which is oxygen gas, that is naturally how oxygen gas comes, right? Our oxygen comes, it comes as a diatomic molecule. It's not really combined with any other element. It also would have a oxidation state there of 0 to start with. Remember that it is only when these two guys come together that they actually do gain some charges, right? And when the magnesium, the oxygen come together, we make an ionic compound, and the magnesium on the right-hand side is group number 2, which means it has a +2 charge. And oxygen here is group number 6 there, which means it has a -2 charge, our oxidation state. Any questions on how I got those numbers? So again, we could use our sort of number line here to make it really simple to figure out, who's being oxidized, who's being reduced. If we started with the magnesium, it started on the left-hand side at 0, which would be right there. And on the right-hand side, it ended up at +2, which means it is moving in that direction. That means the magnesium is doing what? It is being oxidized, yeah. It's becoming more positive. By default, that's really all you have to figure out, because by default, that would mean that the oxygen here is actually being reduced. And we could actually figure it out for the oxygen by doing the same thing. If we look at the oxygen on the left-hand side, it started at 0. And on the right-hand side, it ended at -2, which means it is moving in this direction and becoming more negative and going through reduction. So it's a really simple way just to draw an arrow to the right or to the left there, and you could really quickly figure out something is being oxidized or reduced. Any questions on that there? So what is really happening here is the magnesium, as we know, is giving up the electrons over to the oxygen, and that is where it happens. Yeah. Yeah, so any element that you take basically from the periodic table that is not combined with anything, just by itself, has no charge. It's always 0. Yeah. Yeah, so peroxide, it won't come across here. For example, hydrogen peroxide would be kind of the only one where you have that, and that extra 2 finds its way in there because it's really peroxide, which is -1 actually. So if you happen to have this, so for example, if we looked at hydrogen peroxide here, and we assign the oxidation states here, the oxygen here actually would be -1, and the hydrogen here would be +1 in terms of its oxidation state, as opposed to if you had something like water, where that oxygen is not peroxide, it's basically just oxygen. This would be -2, and this would be +1, yeah, in terms of their oxidation states. Other questions on that? Okay. I would say probably 99 times out of 100, you see oxygen is the -2. Yeah. Occasionally that peroxide will jump in there. Other questions on that there? Okay. Now we did a little bit of that. So when we look at something like this as well, this is our sodium and our chloride coming together to make sodium chloride, and that electron totally missed. But once again, if we were to assign oxidation states here, that sodium there, which is uncombined, would have no charge or 0 oxidation state. The chlorine also would have a 0 oxidation state. Again, that's naturally the way chlorine comes. When those two guys come together, that is when the sodium will pick up that +1 charge. And that is when the chloride here will pick up the -1 charge. So once again, we can figure out what is going on by just doing our number line here. And again, if we look at our sodium, started at 0, ends at +1, which means it is becoming more positive and is going through oxidation. And our chlorine started at 0, ending at -1. Again, going to the left there, becoming more negative. It is going through reduction. So what's happening here is, as we see, my electron missed there, but the electron there is being transferred from the sodium to the chlorine. By the way, this is always what should happen when we have a metal and a non-metal together, right? As we talked about, metals are typically the ones that will lose electrons. So they typically should be the ones that get oxidized. And non-metals are typically the ones that gain electrons. That's, again, how an ionic compound is formed. So whenever you have an ionic compound, basically, that's from a metal and a non-metal, that is always the one being oxidized. Non-metal should be the one being reduced and gaining the electrons. We could actually split this reaction off into 2 reactions to explain sort of what's happening. In this particular case, it is our sodium that is going to 2 sodiums over here, plus 2 electrons. And it is our chlorine here that is picking up a couple of electrons and making this guy here. So these are what are referred to as half reactions. The top one demonstrates the oxidation half reaction. And the bottom one demonstrates the reduction half reaction. They are half reactions because, frankly, when you add them back together, you get the overall reaction of what's happening. So they're half of what is going on. We also see as well that the number of electrons here, if you do everything correctly and balance correctly, should always be the same in both half reactions, because in this case, there's actually two sodiums, right? And each sodium is losing one electron, which is why there's two electrons. There are two chlorines, right? And each chlorine is gaining an electron. So again, that's why there are two electrons. So again, when you write these half reactions, or if you see these half reactions, they always should have the same number of electrons in each one before you add them back together. The other thing that we know is the electrons on the left-hand side represent a reduction half reaction. So whenever you see electrons on the left-hand side, it is like they are gaining them. So that represents a reduction half reaction. Whenever you see the electrons on the right-hand side or the product side, that represents an oxidation half reaction, as like they're being given off or lost, basically. So that's why they become like products in there. So when you have these two half reactions, like I mentioned, you basically can add them back together to get the overall reaction. And when we add it back together, anything that's on opposite sides of the arrow that are the same could cancel or reduce. The one thing that should always 100% cancel out is the electrons. So the electrons always need to be the same on both sides. If they are not, you need to multiply one by a number. But in this case, they will cancel out completely. Then everybody on the left-hand side stays on the left-hand side of the arrow, and everybody on the right-hand side stays on the right-hand side of the arrow. This sodium ion and chloride ion will come together to make our ionic compound of sodium chloride in this case. Any questions on that there? Now, what I was talking about earlier, when you take these half reactions, let's just say you wrote a half reaction like this. And you had your other half reaction here of our 2 electrons plus our Cl2 that goes to our 2Cl minus. So if I wanted to add these back together at this point, the way they are right now, I could not do it because the electrons in both half reactions are not exactly the same. And this sometimes happens if you have half reactions given to you or something like that. What you need to do in this case would be to multiply this half reaction by 2. And that would give you your 2 sodium goes to your 2 sodium ions plus your 2 electrons. Now what you could do is add back together the reactions at this point, these two guys, and you obviously will get back down to here. So sometimes what happens with half reactions is before you could sort of add them together, you may have to multiply one of the half reactions by a number to get the electrons the same, or sometimes you may have to multiply both half reactions by numbers to get them to the same. But whatever happens, you do want to make sure that they are the same number of electrons before you put them back together. Again, the idea here is that sort of complete transfer of electrons from one thing to the next to result in that. Any questions on that there? So here's our magnesium example. And just to illustrate sort of the idea of what we saw here with our chloride, which is -1. For example, if we had ClO3 minus, for example, right? This is a covalently bonded guy. We got 7 plus 18 plus 1. That's like 26, I think. So if we were to draw the Lewis structure of this, will look something like this, I believe. I did my math right there, hopefully. So in this particular case, this chlorine, if we were to sort of assign oxidation states, the oxygen here in this case is just oxygen. So it would be -2. This would be -2. And this would be -2. And when we add up the oxidation states, they do need to equal the overall charge on the ion. If it does have a charge, R if it's neutral, it needs to equal to 0. So in this particular case, if we added up all the oxidation states for the oxygen, that is -2, 4, and 6, plus our chlorine will equal -1. In this particular case, the chlorine has what type of oxidation state? What would get us to -1 for the chlorine? Chlorine would have to be +5 in this case. So the chlorine here would actually be +5 in this case. And again, that is because in this case, it is not a ionic compound where the electrons have been completely transferred. Here it is sharing electrons with a bunch of oxygens, which is maybe slightly more electronegative than it, and is going to bring the electrons closer to those 3 oxygens and making the chlorine in this case take on a more positive sort of charge because it's sharing electrons. So again, this is just a reminder that oxidation state is different than, again, those sort of charges we think about when we talk about ionic compounds. But if it is an ionic compound like we have up on top with sodium chloride, it will be its normal sort of charge that you think about. But if you're dealing with something that is covalent, it will take on a different sort of oxidation state because there's those sharing electrons and those electronegativity values. Any questions on that there? By the way, you don't have to draw it to do this. You can just, go that's -2, that's -6 equals -1, and then do your +5. You can kind of figure it out, obviously, without drawing. You don't need to actually draw it or anything. All right. All right, so here's our half reaction for our magnesium oxide. And again, as I mentioned before, one is an oxidation half reaction where we are losing electrons. And obviously one is a reduction half reaction where we are definitely gaining electrons here. So as I mentioned before, probably won't use it too much, but those other definitions involving oxidation reduction sometimes works really well for things with nonmetals and nonmetals. So in this particular case, we can see that the sulfur here actually gains some oxygen as it goes from left to right. And that means that it is being oxidized, while the oxygen here is actually being reduced. I tell you what, why don't you take a second and see what you come up with? Why don't you figure out the oxidation numbers for each of those elements in each of these guys? So what is the oxidation state of the sulfur, the oxygen, the O2, the sulfur, and the oxygen? See what you come up with. Okay, let's take a look. So whenever you got oxygen, definitely the place to start with if you want to sort of assign oxidation states to sort of figure out what's going on. So the oxygen here on the SO2 would be -2, and there's 2 of them, which kind of gives you an overall -4 sort of charge. In this case, SO2 is actually neutral, which means it needs to add up to 0, the oxidation states, which means to get us to 0, the sulfur in this particular case actually has a +4 sort of oxidation state. Again, different than the -2 that we normally think about with sulfur and an ionic compound. Here it is +2 because it's sharing electrons with the oxygen, which again is more electronegative. So it's going to make it more positive as those electrons are kind of unequally being shared with the sulfur, and it takes on a positive sort of charge. The O2 is oxygen, how it naturally comes. So it is combined with anything. So that is our 0 oxidation state. So that's just going to be 0. Now, SO3, once again, we'll start with the oxygen, which is -2. There are 3 of them, which means that's like a -6. Once again, SO3 is basically neutral, which means we need to add everything up to equal 0 in this case. And in this particular case, it would be a +6. The sulfur is taking that. we actually see the sulfur become more positive in this case because it's now hooked up with not 2 oxygens, but 3, right? Which that third oxygen is going to bring more electrons away from the sulfur and make it more positive in this case. We could figure out what is being oxidized by just following our oxidation numbers. The sulfur started at +4, which is like here, and actually ended at +6, which is going in this direction, right? Becoming more positive, which means, again, it is going through oxidation, the sulfur here. The oxygen started at 0 over here and ended at -2, which would be going in that direction, which means it is being reduced, which is the exact same thing we came up with over here. But that, again, is really what's happening here. By it attaching another oxygen, going to suck more of the electrons closer to that third oxygen, making the sulfur becoming even more positive in that arrangement. Yeah. It's actually O, it's not O2. O2 actually has a 0, but yeah, oxygen in a sense has a -2, and that's how you can work your way backward. And most things will have oxygen. Not everything will have oxygen, but most things will have oxygen a lot of times in it, and you could do that. If it doesn't have oxygen, it will have probably hydrogen, which will be +1, or it will maybe have fluorine, which will be -1 and stuff like that. So just kind of knowing those few little rules that I wrote on the other slide is enough to probably allow you to sort of figure out the oxidation states of everybody, which makes figuring out, what's going on, is it being oxidized or reduced, a lot easier if you kind of can figure that stuff out. Other questions on that? So as we talked about, really are 3 reasons why a reaction takes place: solid being formed and water being formed, which we covered in basically our double displacement reactions. And here in redox, obviously, we are covering our transfer of electrons. So as we talked about earlier with our double displacement reactions, whenever we get 2 ionic compounds together, we're going to get that switch that's going to occur. And once again, that is our positive negative guy, our positive negative. So as soon as you see that arrangement, that is definitely our double displacement reaction, and our positive guys are going to switch partners. Remember, as I think we might have talked about last week, if you need to predict what goes on the other side of the arrow and all you have is on the left-hand side of the arrow, you do want to make sure that you write the correct formulas down first and then balance it. Do not try to balance it at the same time. It is a very common thing. For example, somebody would look at just the front part of this one, where you have K2, CrO4, and BaNO3, 2, and go, oh, 2 and 2. So this is like K2NO3, 2, and they try to balance it when we're writing the formula. This is an incorrect formula. Yeah. So you want to make sure that you get the right formula down first and then balance it. So it's a very common mistake. People try to do both of those things together. Always first the formula, then the balancing aspect of it. So this is, again, a double displacement reaction. More specifically, again, as we talked about, a precipitation reaction because of the solid that's being formed in this case. We also saw this earlier at the very beginning, as we talked about, again, our strong acid, strong base. So again, positive, negative, positive, negative. Our water being formed right there, and our salt being formed. So once again, our salt and water. So again, those two really do fall under the double displacement umbrella. So now let's talk about redox reactions here and what falls under those. So here we do have, again, a redox reaction occurring. If we look at oxidation states here, that is 0. That is 0 because that is naturally how they come. On the right-hand side, when they come together, that is +1 and -1. So once again here, the lithium started at 0, ends at +1, which means it is being oxidized. and this guy would be reduced in this case. So this is definitely a redox reaction that is taking place. We also look here. This type of reaction is what is known as a single replacement reaction. And a single replacement reaction basically has that general formula of A plus BC goes on to the other side. If this was a metal, this would have no oxidation state. This would be an ionic compound. It would come in and kick out the positive guy like we've talked about, make a new ionic compound, and this guy would come out by itself with no oxidation state. If this was a non-metal, which could also happen like that experiment when we did all the halogens, it will actually come in and kick out the negative guy in this case, and it will make a new ionic compound, and this guy would come out with no oxidation charge. So that is your classic sort of single replacement reaction setup. You have either a metal or a non-metal by itself, and you have an ionic compound where the guy coming in replaces it. Remember that the one coming in needs to be more reactive than what it is replacing. So it needs to be more reactive than what is replacing. And if it is not more reactive, then the reaction will not take place. If it is more reactive, then obviously the reaction will take place. So if we look here at this one here, this is a metal, right, which is zinc. This is an ionic compound, which is hydrochloric acid. So this guy comes in, kicks out the hydrogen. When the hydrogen gets kicked out, that we make our gas, like we did the other day, right? Thumb over the thing, burning splint, barking thing, yes. So the bubbles that you see, right, when you make the, if we use magnesium the other day, but it's kind of the same idea, right? You made some bubbles. Those bubbles that you see is the formation of the hydrogen gas, and then we make an ionic compound in this case. So what's happening here is if we look at it through sort of oxidation, you could definitely classify this more specifically as a single replacement reaction. This is still a redox reaction that is taking place. And if we look at our oxidation state, this is zinc by itself, which means it has 0. This is hydrochloric acid, which is +1 and -1. This is hydrogen by itself, which means it has a 0 oxidation state. This is zinc, which is a +2, and a chloride, which is a -1 because it's an ionic compound. So it's the normal charges that we associate with it. If we look at what's happening in this case with the zinc, zinc is starting at 0 and it is ending at +2. So what is happening with the zinc? It is being oxidized, yeah, becoming more positive. When we actually look at the hydrogen in this case, hydrogen is starting at +1, right, which would be here, and it's ending at 0, which means it is moving in this direction. So it's actually the hydrogen here that is being reduced in this case, or going through reduction in this case. Yeah. Yeah, so zinc is an ionic compound. So that's the nice thing. You can just default to a normal ionic compound, what the charges are. So if you have an ionic compound, a metal and a non-metal together, that is when they have charges, and that's when they have our normal sort of charges we think about, everybody. So zinc, right, is one of those transition metals that always makes a +2 charge, and chloride in this case would be -1 like normal because it's an ionic compound. So really they only kind of get the weird sort of oxidation states when it's a covalent compound. So just all non-metals there, and that's when they get those kind of weird sort of oxidation states. Other questions on that? Is there anything happening to the chlorine here? Chlorine is -1 on the left and -1 on the right. There's nothing actually happening to the chlorine. You could actually, if you get that one here, you could actually write a net ionic equation for single replacement reaction as well. It works kind of the same way. And so, for example, we would take the zinc and we would keep it together because it is a solid. This is a strong acid, which means it would break apart into H plus and Cl minus. This is a gas, right, which is covalent, so it will actually stay together as well. And our zinc chloride would break apart into zinc plus 2 chlorides in this case. Our spectator ion in this case, again, is actually just the chloride on both sides. It's actually our spectator ion. This cancels, this cancel, leaves us our net ionic equation of zinc plus this guy going to here plus this. And this really represents the redox reaction part of it that's happening. Again, it's our zinc that's going from 0 to +2, and it's our hydrogen going from +1 to 0. So with a single replacement reaction, and sometimes with a redox reaction, people will write the net ionic equation to show the redox part of it, where somebody's gaining and sort of losing electrons, getting rid of the spectator ions as well. Questions on that? So to be clear here, single replacement reactions is a more specific classification of really a redox reaction. I would say probably 9 times out of 10, if people were given this equation here and they were asked to identify it, single replacement is probably how they would do it, but it still falls under the big umbrella of a redox reaction that's actually taking place. Any questions on that? Another type of reaction is a combustion reaction, and there's really kind of 2 types of combustion reactions. This is more of a traditional organic combustion reaction. And an organic guy is basically carbons, hydrogens, oxygens is an organic compound. So whenever you have sort of an organic guy like methane, that's propane. They basically have these 3 components in the reaction always. On the left-hand side, you got O2, and it always makes CO2 and water. So pretty much if it's an organic combustion, lay up an O2 on the left, CO2 and water is probably always going to be your products, and just balance it at that point. Now, as we talked about in lab, I think last week, really a true sort of generic sort of definition of a combustion reaction is simply the presence of O2. So technically speaking, you could classify a reaction that has O2 in it as also a combustion reaction. So for example, we saw this guy earlier. So technically, this, as we saw earlier, is a redox reaction, because again, it is obviously gaining and losing electrons. It could also be classified as a combustion reaction because it has the presence of O2 there as well. And frankly, as we'll talk about, and maybe we did the other day as well, it could also be classified as a synthesis or combination reaction. So there's actually 3 different ways. For example, this particular reaction, you could classify it. So there definitely is multiple ways to classify the same reactions. Sort of, what you're looking at it, how you may classify it. So keep that in mind. Some people might call it a precipitation reaction, but some others may call it a double displacement reaction. Both correct, yeah. You would choose the best one, yeah, maybe. So I might give you a list maybe to choose from, and then if it's a list, choose the best one for that list. If there's no list, technically speaking, if you laid up any of those 3 answers, they're all technically correct. Just like if you had a precipitation reaction, you wrote precipitation, or you wrote double displacement, is technically correct. Well, yeah. Other questions on that? Yeah. Again, I would say probably we'll talk about this guy in just a second, the synthesis part, but probably most people, if they looked at this reaction, would probably call it a synthesis or reaction. Probably the common way that people would call it. So talking about synthesis or combination reaction, that is, as we talked about, it has a general form of A plus B makes AB. So it's basically putting things together. So two things make one thing is a classic sort of combination reaction. H2O2, two things make one thing. Sodium chloride, two things make one thing, as the one we just saw there a second ago, magnesium and oxygen. Make some magnesium oxide, two things make one thing. So these are all examples of synthesis or combination reactions where we put them together. They are still, again, redox reactions as well. Hydrogen in this case is 0. Oxygen in this case is 0. Oxygen here is -2, and the hydrogen here is +1 in the case of water. So once again, if we look at what's happening with our hydrogen, is starting at 0, ending at +1, so it's being oxidized. And our oxygen is starting at 0 and ending at -2, it is being reduced. And same thing with our sodium chloride that we looked at earlier as well. Sodium from 0 to +1, chlorine going from -1 to 0. Once again, in these two examples here, we should always know it's a redox reaction, because whenever you get the metal and the non-metal together, you get that transfer of electrons. So that's your definition of oxidation. And it should always be the metal being oxidized. It should always be the non-metal being reduced when those two things come together to make an ionic compound. Any questions on that there? So the last one here, I think, should be the opposite of synthesis or combination, and that is decomposition. And it really is the reverse there. It basically is one thing makes multiple things. So again, like you did with the little battery and the little container the other day, run an electrical current over water. One thing makes two things. Same thing here in this case, when we do electrolysis, this is +1, this is -2, 0, and 0. In this particular case, what is being oxidized when we do this reaction? Oxygen starts at -2, right? And ends at 0. So it's actually the oxygen in this case, yeah. And the hydrogen in this case is +1 and ends at 0, heading in that direction, being reduced, because it's the opposite of the previous one where it was switched, right? So when we put it together, we oxidize the hydrogen and we reduce the oxygen. When we go backwards, everything switches to make it go backwards, basically. So they're opposites of each other. But once again, this is still a redox reaction that occurs. So as you can see, there are multiple ways you can classify reactions depending on what you're looking at. So just to summarize again, the different types of reactions here. Under the big umbrella of double displacement, you can more specifically classify a reaction as a precipitation reaction or an acid-base reaction. Under the big umbrella of redox, pretty much follows everybody else. You could more specifically classify a reaction as a synthesis or combination, a decomposition, a single replacement reaction, or a combustion reaction. So pretty much all classifications fall under one of those two sort of umbrellas. And again, you could get a little bit more specific than just this is a double displacement or a redox. Any questions on ways to classify reactions or those